So, hi everyone, good evening. This is me, Dorothy Sachdeva. I'll be your TA for this course of material characterization, which is given by S. Sankaran sir. We'll be having these weekly sessions on Saturdays from 6 to 8 p.m. And I'll firstly discuss about the topics which have been covered by the professor, and later on, we'll discuss about the assignments and quizzes which have been given of the respective weeks. So, if you have any doubts or any queries, you can just ask me. Otherwise, we'll solve every question of the assignment and then we'll move forward. If there is any, are you guys able to hear me? Okay, thank you. So, I'll switch off the video for the better quality of the. Okay, I'll share my presentation. Are you able to see my screen? The presentation? Okay. So I professor have covered the three lectures on this fundamentals of optical microscopy. So I'll just briefly discuss about that topics and then we'll move for the assignment part. So let me take the pointer. Yeah. So my name is Dorothy Sachdeva. I am a PhD student at MRC department in Indian Institute of Science, Bengaluru. So fundamental of optics. So basically we'll cover these major topics in this lecture, like the properties of light and some things about the compound microscope, the diffraction and the interference and the resolution of an image, the depth of field and depth of focus, and how these things are different from each other. Also we'll discuss about the aberration in the lenses. So firstly, we know that light behaves both as the particle as well as wave. So it has a very huge range, starting from the radio waves to the gamma waves. As we go from radio waves to the gamma waves, there is a decrease in the wavelength, or we can say there is an increase in the energy, as energy and wavelength are related to each other. We have generally we say that the velocity of light is related to the wavelength, as c is equal to mu lambda, where mu is the frequency, and using this we see that E is equal to h nu, where h is the Planck constant and mu is the frequency and E is the energy. So using this c is equal to mu lambda, we can say and put the value of mu as c by lambda. From this equation we get that E is equal to hc by lambda, where we can say that as the wavelength of the light decreases, the energy of the light keeps on increasing, just as in this case where the radio waves have the highest wavelength and has the lowest energy. And as we go from radio to gamma, gamma has the lowest wavelength and the highest energy. So basically, uh, we humans have our eye range covers the range of this range only, and depending upon the thing which we need to analyze, different frequencies can be used for the microscopy level. Like if we want to have the if we want to analyze very small particles, then we'll be requiring higher energy of light. And if we want to see humans or other huge things like buildings and everything, then we need to have the higher wavelength or lower energy light. Someone, I guess, is waiting in the lobby. Just a second. Yes. So basically these rays are the electromagnetic radiations, where the electric field and the magnetic field, it propagates in the perpendicular direction to each other, where when the electric field is oscillating in this direction, the magnetic field will be oscillating perpendicular to it, and the wave will propagate perpendicular to both these. Like if the electric field in this direction, magnetic field is in this direction, then the wave will propagate in this direction. This is the basic criteria for electromagnetic radiations. Also we have one Snell's law, where we say that when the light travels from one medium to another, there is a change in the refractive index. As a result, the path of the light changes. So this formula, which is the n1 sine theta 1 is equal to n2 sine theta 2, is used, where we say that the when the light travels from lighter medium to the denser medium, its velocity will change. So it's given by this Snell's law. Then we'll discuss some basics about these compound microscopes, where these compound microscopes have, when the incident light falls on this object, uh, it reflects the light in all directions, and these lenses then transmit the light. Firstly, we have this back focal plane, and then the image is formed at the screen. So basically this back focal plane is your also describes the image, also describes about your object, as in it is this back focal plane will discuss further in the later lectures, but as of now I can say that this back focal plane also tells you about the object. Like in the reciprocal space, if you have heard about the reciprocal space, this back focal plane has the point mapping, and these points will describe about the object, and the image is basically just the magnified version of the object. This is in real space itself, whereas the back focal plane also has the information of the object in the reciprocal space. We have these basically formula for the magnification of the objective lens and the eyepiece, where the total magnification is just given by the multiplication of these eyepiece and the objective lens. Someone else is there, just a second. what what is the periodic object? Slide number 18, which slide are you talking about? Lecture slide. um, do you guys have that slide? Oh, I need to check that slide. After that I can tell you. Okay, can you elaborate it further, or I'll check that, then I'll let you know. Okay. Yeah, I have started the recording, and I'll be posting this recording sessions every week itself. Okay, we'll discuss basically about the assignments and everything. So if you have any queries, you can let me know. Otherwise, we'll do it. You can see the recording. Otherwise, if you have any doubt, you can just ask me. So when the light behaves as the wave, it basically diffracts from the slit. Like we all have studied this single slit diffraction experiment, where a monochromatic light, when falls on the slit, it the light waves diffracted by the slit, and it forms these maxima and minima kind of things, which tells you about the, and these fringes are known as the intensity of the light. So this is basically the diffraction of light from a single slit. Similarly, the double slit experiment is also there, where the light will be getting diffracted from two different slits, and that will result in two different intensity fringes, and the overlap of those two fringes will tell you about the maxima and minima kind of things. And the overlap we can tell about from the interference. Like there are three basically: constructive interference, where the phase, like you can see this orange wave, this is a sinusoidal wave which is going in this direction. Similarly, there is this blue kind of wave, blue wave, which is also having the same, it is having the same lambda and same phase, is just that its amplitude is higher. So the addition of these two waves will give us the constructive interference, where the final wave, this dash dash line, will just be the addition of the orange and the blue wave. And if there is a phase difference, completely phase different, opposite phase, like in this one, the blue one starts from 1 and then it goes to -1, 1 0 1, like this, and the orange one goes from -1 to 1, then these are quite opposite, and the sum of these two will give us the destructive interference. So they are totally opposite. So as a resultant, the sum of these waves will is given by this dash dash line, which will result in the zero intensity. And there will be the partial destructive interference, where there is not complete phase change. So as you can see, the orange one starts from here and the blue one starts from here. So these two are starting from opposite point, but the amplitude of the blue one is very higher as compared to the orange one. As we can see that, let me zoom in. This is the zero intensity, and this is, if we can consider this as the 1, so for orange one this will be the 1, so this is lesser than 1. So if we'll add these two, then we'll get a positive value in the blue side. Similarly, in the other case, this is lesser, this is more, so after adding these two, I'll get an intensity which is in the negative side. So we'll get a resultant intensity which is lesser. So this is partial destructive interference, this is not complete destructive interference. Then we'll discuss something about the resolution. Like basically the resolution, can anybody from you tell me about what does resolution mean to you? Yeah, so basically when a car is approaching to you, and from far you can't say that if it is a two-wheeler or a four-wheeler, because four-wheeler will have two headlights and two-wheeler will have only one headlight. But from far distance you can only see that some light is coming. But when the vehicle is approaching to you, then only you can resolve that there are two lights, headlights or one headlight. So the distance, the distance from which you can resolve two things, that means you can say that these two things are well separated. That is basically the resolution. So in our case, like in this, if these are two humps and they are quite well apart from each other, then they are well resolved if seen from a specific distance. But if they if we bring these two humps close together, then if we bring these two humps very close, such that the intensity which we are seeing, this blue one, is not differentiating between these two humps, then we can say that these things are not resolved. But there should be a minimum distance between these two humps, such that the blue line which we are able to resolve should be these line can say that the two humps are well separated. So these resolution is given by this Rayleigh criteria, where we have this sine theta is equal to 1.22 lambda by d. So this Rayleigh criteria is basically the diffraction limitation. This, in every microscope you will have this diffraction limitation. Even when you have the microscope of very good company and everything, even then this diffraction limitation will always be there. This is just the, yeah. So yeah, so what I was saying, that this diffraction limitation will always be there even when your microscope is of very good company and everything, because this is the basic thing of the light to be resolved. And the resolution is given by d is equal to lambda by 2 Na, where Na is basically the numerical aperture. Yeah, okay. So basically, to increase the resolution, like we told in the previous slide as well, so to have a resolution, that means to resolve two small points, we either should have smaller lambda, or we can say the higher energy, or we should have the larger d, larger distance of the two. Also, there is a slight confusion in every student about this depth of field and depth of focus. So basically, the depth of field is related to the object and depth of focus is related to the image. So depth of field is basically the thickness of optical section where the objects in the specimen are in focus. So if we are able to focus the object, that is the region where the object is in focus, that will be the depth of field. And the image plane where the image is in focus, that will be known as the depth of focus. So some places these depth of field and depth of focus are used interchangeably, but these two things mean one is for field is for object and focus, depth of focus is for image part, that you should remember. Also we have this optical path length, where this I guess he have not taught you yet, but I guess he'll tell you in the next week's session. But this optical path length is basically the number of vibrations which occurs between 2 points. It is basically just the product of the diffractive index in which the light is traveling and the thickness through which it travels. So if we need to find out the path length optical path length difference, then we'll just subtract the from between two different mediums, then we'll just subtract the refractive index of both these, keeping the thickness same. And this you all must have known, that the lens formula is 1 by f is equal to 1 by v minus 1 by u. This is a very common thing. Also, we have learned in this week about the aberrations, where we have the on axis and the off axis aberrations, where we firstly have the chromatic aberration. These chromatic aberrations will occur only if the light is not monochromatic. If the light is monochromatic, that means that the light is having only one wavelength, and that will focus on its that will focus at a single point. But if the light is a white light, then white light is consist of all the colors, so there will be a chromatic aberration, where we can where will say, just a second, yeah, where we'll say that the violet light, which has the higher lambda, will focus very closer as compared to the red light with the higher lambda. So this can be seen in the images, where, so if this chromatic aberration is present in your system, then you will see an image of your object, but there will be a slight around your image, like if I can draw, I'll show you. If your image is like this, then all these colors intensity will be around your system, like your image will be resolved, but the outer shell of your image will have all these ranges of the colors. So this range, if your is colored, then you can say that you have the chromatic aberration in your microscope. Next, we have this spherical aberration. Spherical aberration also occurs when the lens, when the light is not transmitted to us, is not focused at a single point. So the light which is, so this is the optic axis, the gray one. So the light rays which is traveling closer to the optic axis will focus at a certain point, and the light rays which are far away from the optic axis, like this one, let me take the pen and show you very clearly. So this is your optic axis. So the light rays which are closer to your optic axis will focus at a certain point, like this one, and the rays which are far apart from your optic axis, like these two, then they are focusing at this point. So this is their focal plane, and for the closer one, this is their focal plane. So this region is basically having the, so there is not specific single point where each and every ray is focusing. So there is this which is known as the region of wait a second, someone is there. So in this region your image will be blurred, somewhat blurred, and your, this will be your uh, disk of least confusion. This distance will be your disk of least confusion. So also we have this off axis aberration, where we first have this comma. This comma is basically the asymmetrical spherical aberration, where the non-axial points, like these points, get elongated when they are diffracted from these lens. Sorry, sorry. Yeah. So in this comma aberration, the non-axial points, like this point, will get elongated, and it will form a comet shape. Like this point will get first diffracted. All these rays will get diffracted from the lens, and they will focus at different points, and as a result it will form a comet shape kind of things. So this is the coma aberration. And then last one we'll discuss is the astigmatism. So astigmatism is basically when so basically if this is your lens, where is my pointer, just a second. Yeah, so if this L is your lens, the oval shaped one, and this blue one is your uh, this blue one is your tangential lines, and this red one is your sagittal lines, then the rays which are transmitted by this is focused at different point, and the perpendicular red one is focused at different point. So these two different focus points of this tangential line and the sagittal lines will make two focus, like this S1 and the T1. So basically our aim is to make these two focus point quite close to each other, such a way that we get a one focal point, and as a result the astigmatism will be reduced and we can get the good quality image. So basically this is all the summary which he had taught you in this week. So is now, shall we start assignment? Shall we start the assignment? Basically you have two assignments now, one is that quiz and one is that practice assignment. Okay, then the first one will start with the practice assignment, which have these 5 questions in total. So the for the practice questions of week 1 assignment 1 is identify the correct statement which depicts the relation between the E and lambda. We all know that we have all known from our study that E is equal to h nu, and nu is from C is equal to mu lambda. I should write it. C is equal to mu lambda. So using these two equations we can say E is equal to h C by lambda. So the correct statement for the relationship between E and lambda will be, the first option is E increases with lambda increases, which will not be correct. And the second option is E increases when lambda decreases, which is true. That whenever will, because they both are inversely proportional. So option B will be correct for this one. For the second question, which of the following statement is not correct? Speed of light is not correct. Just keep this in mind. Speed of light will change when passing from one medium to another is called Snell's law. We already discussed this law, so this statement is true. And the second one is when light passes from high density medium to a low density medium, its velocity will increase. This statement is also correct. When light will pass from high density to low density, its velocity will increase. In denser medium, the light has a lower velocity, but in the lighter, like in the air, it has a higher velocity as compared to some dense material. And the third statement is when light passes from high density medium to a low density medium, its velocity will decrease. This statement is incorrect. So here not correct will be option C. The third question is, which of the following have the highest resolution? First option is the human eye. If the human eye have the highest resolution, then we won't be requiring any microscopes or everything to look at our things. This will not be correct. Second one is the optical microscope, and third one is the glass lens. Glass lenses are used in the optical microscope. The combination of these glass lenses are used in the optical microscope to have a higher resolution. So option B will be correct. The fourth one is the range of position of an object in which the image sharpness does not change. So just look at this where they are saying that image sharpness does not change. So as we discussed in our slide, that image will be related to the depth of field, and depth of focus is related to the object. So this is related to your object and this is related to your image. So the range of position of an object in which the image sharpness does not change. So image sharpness will not change in the depth of field. So option A is the correct answer. And the final question of this practice assignment is, the best possible resolution of an optical microscope is about, uh, can anybody tell you? Can anybody tell me about this? Do you have any idea? Yeah, it is correct, because earlier it was less, but nowadays it is zero point 0.1 micrometer. And if you want to go further, then you need to go from optical microscopes to electron microscopes, like the SEMs and TMs kind of things. So do you all got these 5 questions, or do you still have doubt in these questions? All these things are clear to you? Okay, okay. Then you can have your calculator or pen paper or something like that with you, so that we can proceed to our next assignment where we need to solve certain kind of things. So then we'll move to the quiz of the first week, where they have told, find the numerical aperture and the resolution limit for light having the wavelength of 700 nanometer in pure water, where mu is equal to 1.33 and a cone angle of 70 degree. So this cone angle is basically, sorry, this complete angle. But we know the numerical aperture Na is given by, does anybody know this formula of numerical aperture? Yeah. n sine alpha or n sine theta, where alpha is only this theta. But they have given the cone angle as 70 degree. So first we need to divide it by 2. So n sine alpha will basically will be 1.33 into sine 35. So I'll just calculate this. Have anybody calculated it? Yeah, yeah, it's coming around 0.7628, so it will be around 0.763. So 0.763, and also they have asked about the resolution limit. The resolution limit also we discussed in our slide. I'll first remove this. The resolution limit D is also given by 1.22 lambda by 2 Na. Or some places it's written simply as 0.61 lambda divided by numerical aperture. Just now we found that numerical aperture is 0.763. So and the wavelength is 700 nanometer. So while putting these values in this formula, we'll get the limit of resolution to be 0.61 into 700 divided by numerical aperture, that is 0.763. So it will come around 559.6. So that will be around 560, and the units will be this nanometer only, because numerical aperture doesn't have any unit, and this is also just a numerical constant 0.61. So the value of resolution will be the dimension of this resolution will be equal to the dimension of this wavelength. So the correct option will be option A, 0.763 and 560 nanometer. Any doubts, or it's clear now? So for the second question, we have, for an optical microscope, the focal length of an objective lens is 40 millimeter. The focal length of eyepiece is 10 millimeter, and the total magnification is 50x. Find the tube length if the distance of distinct vision is 100 millimeter. So basically, in this case, we have the focal length. I'll write here only. So basically, we have focal length of objective, we have focal length of eyepiece, We have magnification M. We need to find the tube length L. And also there is the distance of distinct vision, which is the minimum distance from where to, like for our eye the distance of distinct vision is 250 mm, and in this case they have given it as 100 mm. So there is one formula for magnification where we have m is equal to L into this distance of distinct vision. Let me write it as small d, and then the focal length of the objective lens into the focal length of the eyepiece. So using this formula where we have given the magnification as 50x, the focal length of objective lens as 40 mm, the focal length of eyepiece as 100 mm, and the distance of distinct vision D as 100 millimeter. So the unit says 100 millimeter, 10 millimeter, 40 millimeter, all are same. So there we don't need to convert any units. So we can directly put these values in this formula, and then we can calculate the value of L. So let us calculate the value of L. So it will be just 50 into 40 into 10 divided by 100. So that will come as 200, and the unit will be, the magnification doesn't have any unit. These focal length have millimeter unit. This focal length also has millimeter unit, and this distance of distinct vision also has a millimeter unit. So as a result, L should also have a distance of dimension of millimeter. So it will be 200 millimeters. So that means option D is the correct answer in this question. Let's move to the next question. Question number 3. What is the total magnification when using a microscope with an eyepiece lens magnification of 10x and an objective lens magnification of 50x? This also we discussed in our slide, that the total magnification of an objective and object lens and the eyepiece is given as the magnification of an eyepiece into magnification of objective lens. It's basically the product of these two things. So the objective lens has a magnification of 50x and the eyepiece has a magnification of 10x. So it will basically be the product of 50x and 10x that will give you the 500x. So that means option A is the correct answer in this case. So we'll move to the fourth question, which says that for a yellow light, that means a specific wavelength they have given. So that is a monochromatic light. So this is known as the monochromatic light. So can anybody tell me of the which of the aberrations will not be present in this monochromatic light? Yeah, because it is a monochromatic light, so the different wavelength is not at all there. So there is only one wavelength, so it won't be having any chromatic aberration. So for a yellow light, monochromatic, sorry, For a yellow light, monochromatic, lambda is equal to 580 nanometer. Source, optical microscope having medium between the objective lens and the specimen. So the medium is filled with the cedar wood oil, which have the N value as 1.5, and the depth of field. So depth of field is for the object or the image. Are you guys present? Someone told image. Okay, good. So for a yellow light, monochromatic, where we have the wavelength of 580 nanometer source, and the optical microscope is between the objective lens and the specimen region is filled with this oil, which have the mu of 1. N of 1.5, and the depth of field as 0.976 micrometer. So we need to find the numerical aperture and the subtending angle. So can anybody tell me how we need to do this question? Have anybody tried this assignment? Yeah. So basically we had this formula for the depth of field as n lambda divided by Na, that is numerical aperture square. So using this formula, numerical aperture will basically be the n into lambda divided by the depth of field, and the whole will be the under root. So if I'll calculate this value, if anybody have calculated, then let us know. Otherwise we'll calculate that n is 1.5 and the wavelength is given as 580 nanometer and the numerical aperture is in micrometer. So firstly we should convert this depth of field into nanometer itself. So nanometer and micrometer. So if we need to convert this depth of field micrometer into nanometer, we just need to multiply it by 1000. So this point will be, so the point will be, so it will become 976.0 nanometer. So then you can easily cancel out the units. So now the numerical aperture will be 1.5 into 580 nanometer divided by 976. So I will just calculate 1.5 into 580 divided by 976. So that comes at 0.891, and if I'll do the under root of this, then I'll get 0.944. So 0.944. Okay, and the second question is to find the subtending angle. Subtending angle can be calculated using the resolution formula, where we have sine theta value, and then we can find the theta. That will basically be the theta will be the sine inverse numerical aperture divided by n. So this will be sine inverse of 0.944 divided by 1.5. This thing is unitless, so we can apply sine inverse in this. So 0.944 divided by 1.5 is basically 0.629, and the sine inverse of this 0.629 we can't is when calculated the sine inverse of this, it comes out to be 0.671. So this is value is in radians. Now we convert it into degree because the options are given in degree. Then we'll do this 180 divided by pi. I guess someone is waiting in the lobby. Let me ask them to join. In the meanwhile, you can just calculate this value and tell me what is the final answer. Have anybody calculated this value? 39. Okay. So the numerical aperture value we found out as 0.944. That means 0.943. It comes around 0.943, and the angle is 39 degree. So option B will be the correct answer. Any doubts till now? Okay, good. Now we'll move to the next question. That is the fifth one, where we need to find the resolving power of instrument can be increased by. Resolving power means two separate objects which are seen as separate kind of things. So the question is the resolving power of an instrument can be increased by. So the option A is using an illumination of a longer wavelength by a decrease in numerical aperture. And the second option is using an illumination of a longer wavelength. So if we need to resolve two things, we told this in our previous slides that if we want to have a higher resolution, like if we want to see larger buildings, that require lower resolution, but if we want to see atomic nuclei, then we require a lower wavelength, higher energy kind of things. Someone is again waiting in the lobby. Just a second. The session was starting time of the session was 6 o'clock, no? Then why some of people are joining at 7 p.m.? Were you guys confused, or can you please tell me? No response. The session is from 6 to 8 p.m., no? Some people are joining at 7 p.m. That's why I am asking them whether they were not aware or they are joining late only. Okay, anyways. So for resolving two things, we require a longer wavelength. And for about what about the numerical aperture? The numerical aperture, if the numerical aperture is too big, then we will not be able to resolve things quite easily, because that will have more aberrations. If the numerical aperture is smaller, then we have seen the formula where which we have used in our last numerical, where we saw that sine theta is equal to Na divided by numerical aperture divided by n. So using these two things, we can say that the correct answer for this question will be option A. We are using a longer wavelength and by decreasing the numerical aperture. Which of the following statement is not true? Not true. When focusing the slide, care should be taken not to crack the slide. This is correct, because if the slide is cracked, then we won't be able to resolve things. We'll just damage the instrument and our object. The slide should be placed on a stage with a cover slip on the upper surface. Yes, this statement is also correct, because if you have placed the slide like this, then you need to have a cover slip in order to prevent its movement during your focusing thing. And the third option is, when setting up, adjust the eyepieces to the dimension of your eye. Yes, because you have two eyepieces and that eyepieces should be adjusted according to your eyes. Then you, if you focus, if you have your two eyes in both these eyepieces, then you will be able to see the image very clearly. And the fourth option is, always view your specimen using the highest magnification lens first. This option is incorrect, because we should always start from lower mag and then we should increase slightly the magnification from lower mag to higher mag, because the lower mag, it will be very easy for us to do the focusing and everything. And as we go from lower mag to higher mag, there will be a lot of astigmatism and lot of focusing will always be there. But as we go from lower mag to higher mag, there will be a lot of astigmatism, so we need to correct all these astigmatism kind of things at higher mag. So we always go from lower mag to higher mag, not from higher magnification to lower magnification. So in this case, option D will be correct. But you should remember one thing, that if your object, if your image is focused in the higher magnification, then you can easily go to low mag, and then your image should be remain focused in the lower mag itself, because at higher mag you have corrected more things for the image correction. So that correction should also work for your lower magnification as well. This was just a side thing, not related to this question. So from this, so in this question, option D will be correct. That way, that is, always view your specimen using the highest magnification lens first. So this option is incorrect. Rest all these three things are correct, and you should just remember these things while doing your imaging. So your next question is, you place a specimen under the microscope and notice that parts of the specimen begin to emit light immediately. These materials can be described as. Anyone from the students can tell me about this answer? That is very easy one. Yeah, the first option, fluorescent, is the correct answer for this question, because this fluorescent will emit light immediately. The transparent will transmit all the light, and the opaque will not at all transmit any light and will not emit any light on itself. So option A is the correct option. Then we move to question number 8, which says that which of the following has highest energy? Highest energy, highest energy. If we listen about this highest energy, then we can say, then we need to find the lowest wavelength. If you are working with the light and everything, you should know that energy is related inversely proportional to the wavelength. So first option is light with a longer wavelength. Light with a longer wavelength will have a lower energy. The option B is light with an intermediate wavelength will also have intermediate energy. Light with a shorter wavelength will have the higher energy. And the option D says it is impossible to tell from the information. No, we know the formula that which we have studied as well as used in our previous numericals, which says that E is equal to H C by lambda. So this E and lambda are inversely proportional. So when we have the shorter wavelength, the energy will be the maximum. So in this case, option C will be the correct answer. Any doubts till now? Everything is clear to everyone? Okay. Now we'll move to our final questions, where we need to calculate the optical path length difference. So basically this, I guess he have the optical path length, his topic is covered in this week, or it will be covered in the coming week, I guess. Is it covered? Has the professor taught you about optical path length? I guess he'll be covering this in the coming week. So yeah, okay. But this question is there, so we'll discuss about this question, then we'll move for the next one. So the ninth question says that calculate the optical path length difference. So first we need to know what is the formula for the optical path length. So optical path length, basically OPL. We write it as OPL. And this optical path length, when the medium is different, then the optical path length is, yes, just a second. Sorry for that. I'll share it again. Are you able to see it now? Are you able to see question number 9 and 10 on the slide? Okay. Okay. So we need to calculate the optical path length difference. So first we need to know what is the optical path length. So optical path length is basically given by the refractive index, that is n, times the distance which it travels, that is the basically is the thickness. Through which it travels, n into thickness. So using this diagram we can see that the n is 1.5 in this case here, and here the refractive index of the medium is 1.33, and the thickness through which it travels, the thickness is 2.02 micrometer. So using this, we can say that optical path length for this medium will be 1.33 into 2.02, just a second, 1 point, sorry, yeah, 1.33 into 2.202. You all know that this refractive index doesn't have any units, only this thickness have the unit. Micrometer. And for this one, it will be, optical path length will be 1.5 into 2.02 micrometer. So we have to find out the difference between these two. So we'll just subtract these two values. So we can take 2.02 common, 2.02 common value, and then we can subtract 1.5 from 1.33. So this is 0.17. 0.17, then we'll multiply it by 2.02, so it comes around 0.3434, and the units will be of this 2.02 only, and that was micrometer. Yeah, so option B will be the correct option, that is 0.343 micrometer. Just always remember these units, never get confused. If the units are very different, then first convert the units, have the similar values of these units, and then only proceed with your numerical part. So then this question is clear to everyone. This, I guess, will be covered in your next lecture, but the basic thing was to know about this formula, where the objective where the optical path length is basically the product of the refractive index and the thickness. Is this question clear? Okay, okay, thank you. The slides are visible, no? Okay, 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 thank you. Mm-hmm. Someone is again there in the lobby, just a second. Yeah. Why are you joining so late in the class, if I may ask? Who joined just now? I am asking you, why have you joined so late the class? Vishnu, are you there? Okay, we'll move to our final question. The final question is like calculate the position of the image and its magnification when an object is held on 10 centimeter from the convex lens of focal length 8 centimeter. All of you know the difference between the convex lens and a concave lens. This kind of mirror is a convex lens. This kind of lens is, sorry, it's a convex lens, and this is the concave. Basically, this is the convergent lens where the light rays get converged. This is the convex lens, and when the light rays are coming through the concave lens, they diverge. That's why it is known as the divergent lens. My drawing is too bad. I hope you are able to understand the difference between the convex lens and the concave lens. So they have someone is in the lobby again. Jay Lakshmi, why are you joining so late in the class? Hello. Okay, but do you know that this class was about to start at from 6 to 8 p.m., no? Okay. Okay, okay, okay. Yeah. So we have discussed all the basic topics covered by the professor, as well as we have discussed about the practice assignment. Now we are just concluding our final quiz assignment. So the final question is to calculate the position of image and the magnification when the object is held at 10 centimeter. So the distance of object, that is u, is given my writing is very bad in this. So basically the object is held at 10 centimeter. That means the value of u is given as 10 centimeter for a convex lens. And the object is placed on the left hand side. So we can say that it is minus 10 centimeter. And the focal length f is given as 8 centimeter. So the units are same, so we don't need to worry. There is one formula that we all know, which is used to calculate the focal length of the lens and to find out the relation between the object and the image distance, where 1 by f is equal to 1 by v minus 1 by u. So if we need to calculate 1 by v, that will be, so this minus 1 by u will go there and it will become plus, so it will become 1 by 8 plus 1 by minus 10. Sorry. So if we take the LCM and solve this, then it comes about, LCM will be 40, so it comes around 1 by 40. So then we have our V as, what will be the unit? Unit will be the same, centimeter. So it is so position of the image is 40 centimeter. First part is clear. Then we'll move to the second part to calculate its magnification. Magnification in this case is how much the image is magnified as compared to the object. So it is basically the ratio of the size of the image to the size of the object. This is magnification, and demagnification will be how much the size of the image is decreased. Sometimes we need to decrease the size of image and sometimes we need to increase. So in major cases we need to increase the size of image. For that we use this term known as magnification, where we use all these lenses. So magnification is given by the position of image divided by the position of object. So position of image we have just now calculated as 40, and the position of object is already given to us as 10. Both have the same unit, centimeter by centimeter, so they'll cancel out each other. As a result, we'll get magnification as just a single value of 4. So the correct option for this case will be the option C, where the position of image is 40 centimeter from lens and the magnification is 4. Is this clear? Any doubt to anyone? Everything is clear? Oh, someone was typing in the typing. I was not able to see. Sorry for that. Minimum separation between the image. You guys need to. Yeah, can you please tell me the difference between the depth of field and depth of focus? So basically, the depth of field is used for the object. That means uh, in which range we can, like I showed you my slide, no? Just now, let me share my slide. Don't. Yeah. So depth of field is basically the related to object, and depth of focus is related to the image plane. So depth of field, the definition for depth, some places they might use these two as interconvertibly, but you guys should remember that depth of field is basically the thickness of optical section where the objects in the specimen are in focus. When the object is in focus, then only our image will be in focus. First of all, you need to know these kind of things. And the depth of focus is related to the image plane, like how much the image is in focus, and depth of field is how much the object section is in focus. When we'll go further for the for higher microscopy like the SCM and TM, then also you'll come to know about these two kind of things, depth of field and depth of focus, where you'll see that in SCM, whenever we'll decrease the distance, no, like the minimum distance, like here we call this as the distance of distinct vision, there it will be called as the working distance. Then we'll say that whenever this distance is decreased, the depth of focus will decrease. So have you ever tried, like have you ever tried to keep your hand in front of your eye, very close to your face, and then you will only able to see the fine lines of your hand, but you will not be able to see any of the objects which are placed around which are placed around 50 centimeter in your from your eye, 50 or 100 centimeter you can say. So if you are placing your palm very close to your eye, you can see the fine lines of your line hand, but you will not be able to see the object placed on your table at the same time. So now your depth of focus is on your palm itself, but when you place your palm and your table quite far apart, then you can have much more things, but you will not be able to see your the lines on your palms. So these things will come later on in the lectures, but I just wanted to make it clear to you that whenever this distance is increased, then your vision will increase, but your resolution will not, resolution will decrease. Do you got my point? That when you are looking at the palm itself while placing quite close to your eye, then you are able to resolve the lines, even the lines in your palm. Then you are having a good resolution, but your depth of focus is very poor. That means the two things which are just behind your hand you are not able to see. But when your hand and that things are quite far apart, then you can see a lot of different things as well. In comparison to your palm, your table, your laptop, your book, you can see everything at a single point, but you will not be able to see the fine lines on your hand. So in this case, the resolution of your eye is decreased due to the distance from which you are seeing. So this basically tells you how the resolution and how the depth of field are related. So you can have, you need to have the, either you can have a good resolution or you will have the good depth of field. This all things will come later in the lectures. Then you will come to know that we need to compromise between these two things according to our requirement, then only we can move forward. Any further doubts? Okay, were you guys able to understand me clearly, or do you want me to add anything or something, some comments or some suggestions? Okay, so okay, thank you. So those who came late, yeah, please tell me. Yeah, I share the PPT along with the questions, and all these PPT link will be shared with you. I guess I need to share this in my weekly logbook, I need to ask whether that link will be available to you guys or not. But I'll be sharing this recording as well as the PPT. Both these things I need to share. Yeah, for those who came late, myself Dorothy Sachdeva. I'm an PhD student in MRC department in Indian Institute of Science, Bengaluru. So I'll be doing the TA-ship for this material characterization course, which is given by S. Sankaran sir from IIT Madras. So if you have any doubts or queries, you can just ask me in the class itself either, or if I'll be not be able to answer, I'll try to give you answer in the next class itself. If you have any queries, we can have, otherwise we'll leave as of now. If you have any doubts or any queries, you can ask. Srinivas, are you there? Do you need to ask anything? क्या हुआ? बट बोलने वाले थे ना तुम कुछ। तो अभी एक्स2 आप डाल ही नहीं रहे हैं ऐसा? आप कराए दोपहर में जाके उनको सबमिट? तो हमने जो दिया था वो क्यों नहीं दिया?